Hi everyone, my name is Yuting Xiang. I come from University of Connecticut. I'm very glad to present my paper, A Novel Approach to Modeling of Production System, a case study at a small medium-sized manufacturer. First, I'm going to give a brief introduction for the research background. With the development of Industry 4.0, data-driven modeling analysis becomes more and more popular in manufacturing research and practice. In current research, production system is typically modeled as a stochastic process where the operations are characterized by randomly distributed uptime, downtime, and cycle time. The conventional approach to determine the parametric system model is to collect the standard data from each individual workstation and extract the model parameters by aggregating those data. There are many limitations, especially to the small and medium-sized manufacturers. First, most small and medium-sized manufacturers do not have automatic data collection equipment enough workforce to record operation centers data. Second, data from different equipment are in non-standard forms, so no standardized work or unique solution to analyze those data and extract the model parameters. Moreover, due to the different sources of noise in an industrial environment, the inconvenient data cleaning work is involved. Therefore, a new modeling approach is developed and applied, in which the model parameters are identified based on the standard system performance metrics derived from parts flow data instead of the non-standard operation data. On factory floor, parts flow data are much easier to collect using the sensors and the low noise exists. These performance metrics are consistently defined and can be computed in the standard ways. Thus, users at different knowledge levels can easily handle it. In this paper, we studied a production system from a local small manufacturer which designs and produces medical device. According to Figure 1, there are two work cells in this production system. Both work cells have two parallel lines which split the workload and carry out identical processing work. In each parallel line of work cell 1, there are three consecutive operations. The parts are processed from work cell 1 are then placed on the buffer to move to work cell 2, in which there are two consecutive operations in each parallel line. In this production system, the operations have different processing time, so we call it an asynchronous system. In this case study, we first construct a mathematical model for the production system based on the layout and collected parts flow data. Then we use a mathematical model to analyze the baseline performance. Finally, based on the system model and the baseline analysis, we investigate the improvement actions to enhance the system performance. First, we do the structural and parametric modeling. Based on the system layout, we built the complete model as Figure 2. Since no buffer are inside the work cells, the operators in the same work cells are expected to work synchronously. Then we further aggregate the operations in each work cell to reach the simplified model. For the system parameters, we assume the buffer capacity is known because it is easy to collect on factory floor. And we assume the machines have exponential reliability, so the parameters we want to identify include processing speed, breakdown rate, repair rate, and machine efficiency of the aggregated machine in the simplified model. For mathematical modeling, we first review the data collected. We measure the buffer capacity is 15. The reliability parameters of each operation were not available due to the challenge discussed in the introduction. The average cycle time of each operation were as data 2. And using the parts flow data, we can obtain the performance metrics as result 3, where These performance metrics are defined as follows. Throughput is the average number of parts produced by Voxel 2 per time unit during steady state. Working process is the average number of parts contained in the buffer during steady state. And P0 is the probability that buffer is empty, and Pn is the probability that buffer is full. With the data collected, next step is parameter identification. Since we know the processing speed of each operation, the aggregated processing speed can be obtained as formula 4. And then, to obtain the aggregated machine reliability parameters, we solve the constraint optimization problem 5 to minimize the two-norm error. That means we want to find the machine parameters that can best match the performance metrics based on the analytical expression of these performance metrics in the two-machine line model. To solve this optimization problem, we developed a multi-start modified projected Quotient-Newton method. Given a set of performance metrics as input, we randomly select the initial points from the constraint set and initialize the gradient scaling matrix. With each initial point, we update the solution by steps in a while loop. First, we find the appropriate step size for the projection arc by Amiho rule. Then we compute the projection arc and compute the feasible direction, and then we update the solution. Then we separate the variables into two groups, restricted set and free set, as defined in Formula 10. The Quotient-Newton type gradient scaling only applies to the free variables, and the restricted variables descend along the gradient direction. After updating the gradient scaling matrix, we come back to check the convergency. If it is converged, we output the solution as a candidate and move to another different random initial point and repeat this algorithm to get another candidate. Finally, the optimal solution is one of the n candidates who leads to the minimum of the objective function. In this case study, we have data 12 as input. Use the algorithm we developed, we obtained result 3. To evaluate the identified parameters, we compute the estimation error of performance metrics resulted from the identified parameters, and we get the errors are very low, which means the identified parameters can fit the system very well. Next, we want to identify the system bottleneck. With the identified model parameters, we can get the blockage of Voxel 1 and the starvation of Voxel 2 using the two machine line model. Therefore, we get Voxel 1 is the system bottleneck. Next, we discuss the improvement of system throughput. The first way to increase the throughput is increasing machine processing speed. Since Voxel 1 is the bottleneck, we prefer to increase the operation speed of Voxel 1. Figure 3 shows the effect of increasing aggregated speed on the throughput, and we find the corresponding points of our defined minor, median, major, and maximum improvement. Table 1 is showing the detailed improvement plans and operation speed up in Voxel 1. The second way to increase throughput is increasing buffer capacity. Figure 4 is showing the throughput increase and the buffer expansion. Moreover, reducing machine downtime is another way to increase the throughput. Since no uptime or downtime data of each individual operation is available, to study the effect of each downtime change, the first step is to find an algorithm to estimate the parameters of each individual operation. So we assume each parallel line in a Voxel has identical aggregated downtime and down-along throughput, and the consecutive operation in the same line have identical downtime and standalone throughput. The algorithm to identify the parameters of each individual operation in workcell I is as follows. The basic idea is reversely decomposing a workcell. We already know the aggregated E, T down, and C of the workcell. We can first get the estimated E, T down, and C of each parallel line using formula 15, and then compute the E and the T down of each consecutive machine using formula 16 as the estimated parameter of each individual operation. The identified parameters are shown as result 17. Due to the parallel structure in both workcells, we reduce the downtime of the operation carrying on the same processing work at the same time. For instance, we reduce the downtime of operation 111 and 121 together. With the same reduction factor, reducing the downtime of cell 2 leads to the larger throughput improvement as shown in Figure 7, and the maximum possible throughput we can get is about 4.5% higher than the baseline. Finally, we do the model sensitivity analysis. Although the parameters identified for the simplified two-machine model can perfectly fit the observed system performance metrics, it is important to show whether the model is still robust when some model parameters are changed for improvement. We first search for a set of machine parameters that leads to the same performance metrics under the 10-machine model, which is data 18. We call it the true system parameters. We change the processing speed, operation downtime, and buffer capacity to mimic the possible improvement scenarios. With the new Cs, T downs, or Ns, the estimated performance metrics are computed based on the two machine line model and compared with the performance metrics resulted from the true parameters using simulation. Figure 8 to 10 are showing the throughput and working process errors under the processing speed up, downtime reduction, and buffer expansion. We can see our approach can predict the performance metrics in the high accuracy not only under the nominal parameters but also in a reasonable range of parameter change without any knowledge of downtime or uptime of individual machines. Such properties is very critical in designing improvement projects in the manufacturing practice. In this paper, we applied a novel approach to modeling a production system in a case study at a local small manufacturer of medical device. Specifically, we transformed the complete 10-machine system model into a simplified 2-machine asynchronous exponential line model. The model parameters are identified using multi-start modified projected Quasar-Newton method to match the given performance metrics derived from the collected part flow data. With the identified model parameters, we analyze the baseline performance and develop improvement actions, including the operation speed up, downtime reduction, and buffer expansion to enhance the throughput. Finally, the model sensitivity analysis by comparing the deviation of the model predicted performance metrics to those produced by a reference nominal model. In the future work, we will extend this research to more complex production system models, for instance, the multiple machine serial production lines, the systems with non-McEwen reliability machines, and the systems with assembly operation and rework loops, and so on. Thank you.